Okay, good morning. So we're going to continue our lecture 15 with a Laplace Transform Application. Okay, so for the previous week, we have covered these exercises, this example on the Laplace Transform application. Okay, so we have understand basically the transformation, okay, of the passive components, which include the resistors, okay, resistors. Yeah, and then we have the transformation for the inductors, right? And then we have the transformation for the capacitors. Yeah, so we have covered these topics last week. Yeah, and we have also learned how to transform the circuit, into the S domain, depending on the application, whether we want to use the Kirchhoff voltage law or Kirchhoff current law. So these are the things that we have covered last week, and also a few exercises or 4 examples related to these topics. Yeah. Okay, so we are going to continue our lectures on this example. Okay, so we are given a circuit in figure question 2b, yeah, as given in the slide. So it's given that the VCT is the output voltage that is being monitored. Okay, this is the one being monitored. This is the output voltage, which is measured across the capacitor. S1 is the switch that controls the circuit. Okay, we have a circuit here. So we have the switch here. And it is given here that the capacitor C has 0 initial voltage. Okay, so initial voltage for the capacitor is 0, is given. Right, so when t equals to 0, the switch S1 is closed for a very long time. So initially, the switch is open. Yeah, switch is open, and suddenly at t equals to 0, the switch is said to be closed. Okay, and the circuit said that it is reaching the steady state in that condition. Okay, so it's given that the VT, the input voltage, is 20 volt. Okay, it is 20 volt. Then we have the R1 is 5 ohm. Okay, R1 is 5 ohm. Okay, it's 5 ohm. And then we have the capacitor C of 0.5 farad. Okay, and the question number 1 is to sketch the circuit in the S domain for t bigger than 0. Okay, so for t bigger than 0, we know that it's given that the capacitor C is having a 0 initial voltage, yeah? So which means that for this capacitor C, the VC 0 negative is equal to 0, yeah? Okay, that should be the initial voltage for the capacitor. So from the equations that shall be applied in transforming the capacitor, we have learned that the VCS shall be equals to 1 over SC of ICS, okay? ICS is the capacitor's current, plus V0 negative of S, okay? This is the equation, right? And we know that from VC0 negative is equal to 0, or the initial voltage for the capacitor is 0. So the equations here can be simplified just to be equals to 1 over SC of ICS. Okay, that should be the case, yeah? So which means that there is no voltage source in series with this capacitor. So from this information, we can straight away sketch the circuit in the S domain, in which we can have the source of the voltage. We are given the VT is equal to 20 volts. So we're going to transform it into a S domain. So that should be 20 over S. Okay, so we have learned last week, yeah, because 20 volt is regarded as a step function. So when we transform into S domain, it is going to be 20 over S, right? So we're going to have the resistance of R. Resistance is same. There's no changes on the resistor for the impedance, which is 5 ohm. Okay, and then we have the capacitor. Okay, so the capacitor, as what we have learned just now, there is no voltage source. So the impedance is 1 over SC. So C is 0.5 farad. So we can have it to be equals to simply 2 divided by S. That should be the impedance for the capacitor. Okay, so that should be connected straight away like that. Okay, so that should be your answer for question number 1, which is to sketch the circuit in the S domain for t bigger than 0. Okay, right. Hopefully you understand about these issues, these straightforward questions. Okay, right. So number 2 of the question is to obtain the expression of VCS for t bigger than 0. Okay, for t bigger than 0, right? So for this, we need to use the KVL, okay, because we want to find the VCS, which is the capacitor voltage across the voltage across the capacitor. Okay, so we can have, we need to find the current first in this circuit. Okay, so because in the S domain, so the current flows is returned to be IS. Okay, so use the KVL to find the current. Okay, so we're going to have 20 divided by S shall be equals to 5 of IS, okay, and plus 2 over S of IS. Okay, so our aim is to find the IS, so we're going to have IS shall be then equals to 20 divided by S. Okay, so this can be taken to the left hand side. It's going to have it as 5, oh sorry, it should be equals to S divided by 5S plus 2. Okay, so we can cancel out the S here. So we're going to have 20 divided by 5S plus 2. So sorry, my S and my 5 is about the same. Yeah, it's almost the same in terms of its pattern. Sorry for that. Yeah, hopefully you understand, or you know how the difference between the 5 and S in my answer here. Yeah. Okay, so the answer for the IS should be 20 over 5S plus 2. But this is yet to be the answer because we have to find the VCS, which is the voltage across the capacitor. So from the IS obtained, we can find the voltage here, in which the voltage VS or VCS, okay, it will be equals to this current IS multiplied with the impedance of the capacitor, which is 2 divided by S. Okay, so we're going to have IS 20 over S, and this is 2 over S. So we're going to have the answer to be equals to 40 divided by S 5S plus 2. Okay, because your IS is 20 over 5 plus 2, and multiply with 2S, so we're going to have 40 divided by S multiplied with 5S plus 2. Yeah, so that should be your VCS. That should be the answer for that. Okay, any question for this? No, yeah? Okay, so for question 3, 4, and 5, I'm going to proceed with the next page. Remember the question is to find the final value of VCT, okay, final value for VCT, this value, by using the final value theorem. So this is the properties that we have learned last week, yeah, the final value theorem. Okay, so we have learned that for final value theorem, okay, we can say that for final value theorem, okay, so we're going to have the V of infinite. So V is in time domain, yeah, this is in time domain. So I need to write this is in time domain. Okay, time domain. Okay, that should be equals to a limit of S approaching 0 of S Vs. Yeah, so if you say the difference here, this is in time domain, this is in the S domain. Yeah, so but this is the equation or the theorem of final value theorem that we have learned last week, which enable us to find the final value or the end value of the Vt. Yeah, the end value of the Vt. There is also another theorem which is initial value theorem. So initial value theorem is the theorem that enables us to find the initial value of Vt, which is the V0. Yeah. Okay. So for this, we simply substitute the Vs that we have seen or that we have obtained before. Yeah. So we need to find the final value of VCT. Yeah. Supposedly VCT. So you need to adopt this VCS to be used in this equation. So if I can write back, this should be the VCS, and that should be the VC infinite, yeah? Because we are finding the capacitor voltage. Okay, so we're going to have a limit, okay, as approaching 0, S multiplied with the VCS, which is 40 divided by S, it is 5S plus 2, okay? It should be 5S plus 2, right? 5S plus 2. Okay, so you need to substitute the S as 0, so that should be cancelled out, this S. So by substituting S equal to 0 in these equations here, right? We're going to have 40 divided by 2 only. So straight away, we're going to have the answer for the VC of infinite shall be equal to 20 volt. Yeah, so that should be your final value of the VCT. So if I can rewrite this, this is a VCT. Okay, the VCT for T is infinite. Yeah, okay, that should be your capacitor voltage in time domain. Okay, so is that clear on this? Okay, hopefully it's clear. Yeah. Okay, for part 4 of the question is to find the VCT for t bigger than 0. Okay, so again, we need to use these VCS terms, okay, to find the VCT for t bigger than 0. Okay, because what we have obtained here, this VCS here is the capacitor voltage in the S domain for t bigger than 0. Okay, so to find the VCT, what you have to do, you have to do the inverse of Laplace transform. Yeah. Okay, so I need to rewrite the VCS. So we're going to have 40 divided by S, 5S plus 2. So to find the VCT, we need to write this VCS in terms of a partial fraction form. So we're going to have it as A over S plus B over 5S plus 2. Okay, so we can then find the A and B. Okay, so to find the value of A, multiply both sides with S. We're going to have 40 over 5S plus 2 should be equals to A plus BS over 5S plus 2. Okay, and then you need to substitute S equals to 0. So that we're going to have A as the only variable on the right hand side. Okay, so that should be 40 over 2 equals to A. So by right, your A value shall be equals to 20. Yeah. Okay, that should be the value of A. And then for the B, we are using the same technique, okay, the same method, in which to find the B, multiply both sides. Okay, multiply both sides with S 5S plus 2. So we're going to have 40 over S. Yeah, sorry. I apologize to erase this. Sorry. Okay, so we're going to have 40 divided by S. Okay, equals to A, okay, over S multiplied with 5S plus 2 plus B. Okay, so to find the B, you need to substitute the value of S as negative 2.5. Yeah, so that we're going to have only B on the right hand side. So multiply both sides with S of negative 2.5. So you are going to get the B shall be equals to 40 over negative 2 over 5. So that should be equals to 200, so it should be negative 100. Yeah, so that should be your B value. So as such, from here, you can see that the answer for A and B is 20 and negative 100 respectively. So it should be 20 over S minus 100 divided by 5S plus 2. Or simply going to have 20 over S minus 20 over S plus negative, S plus 2 over 5. Okay, so that should be your VCS in terms of partial fraction. So from here, I believe you can find the VCT straight away, okay, by using the inverse of Laplace transform. So I need to write this first to erase this answer first. Sorry, okay. Okay, so you need to do the inverse of Laplace transform because you need to find the VCT, right? So for here, we're going to have the inverse of Laplace transform. The VCT shall be equal to the inverse of this. Yeah. So we're going to have 20 of UT, okay, minus 20 exponential of negative 2 over 5t of UT. Yeah. So that should be the answer for your VCT. Okay. Is there any question for this? No, yeah. Okay. So let us proceed with this question. Next question, which is number 5, which is to describe the behavior of the capacitor voltage VCT throughout the time t bigger than 0. Okay, this is to describe the behavior of capacitor voltage VCT, which is, in other words, we need to sketch it, yeah, to sketch the capacitor voltage according to these equations. So I believe that from, we have 20 UT. Let me erase this answer first. Okay, we have the eraser. All right, we have for the 20 of UT, the graph for 20 of UT will be simply a step function. That should be the one, the amplitude of 20. And for this 20 exponential negative 2 over 5t UT, so your graph of that can be looked like this, okay, which is reducing exponential. This is 20, so that should be the reducing or decaying exponential. So when we subtract the two, 20 of UT minus 20 exponential negative 2 over 5t UT, so by right, the answer for that will simply a exponential or rising exponential, which will look like this. So that should be 20, yeah? So that should be the graph of VCT. Okay, so that should be the answer for this question number 5. Okay, any question for that? For this example? Yeah.
There are some of our friends waiting for you to admit them to the meeting.
I'm giving them 5 minutes after 11 for them to enter, but since they are late, so I didn't allow them to enter this discussion. Sorry for that. Yeah.
Okay. Thank you, Doctor.
Thank you very much. Right. Okay then. Any more questions for this example? No. Okay. If there's no question, let us proceed with next question, which is on this example on this circuit. Right. Okay. So we are given these problems here. Where the switch, okay, we are given this circuit configuration where we have 100 volt as the input, okay, 100 volt as the input here, okay, and we are given the 10 ohm of resistors, 3 Henry of the inductors, yeah, and it's connected to resistor of 15 ohm and 2 Henry, okay, so these are the connections that we are given. Okay, in this statement here, the switch S is set to close for a very long time and left open for t bigger than 0. Okay, you have a switch here. Yeah, we have a switch here, switch S. Yeah? It's mentioned here that the switch is closed for a very long time and left open for t bigger than 0, which means that initially, or for t less than 0, okay, for t less than 0, your circuit configuration should be a short circuit. Yeah, this is for the case of t bigger than 0. Yeah, for t less than 0, the switch S is set to be closed. Yeah, it's set to be closed, and it's open for t bigger than or equal to 0. Okay, so now hopefully you understand the situation or the conditions of this circuit. Yeah. Okay, so now, based on the given conditions, you have to determine the initial voltage for the 3 Henry and for the 2 Henry inductors, which is the initial, I'm sorry, not initial voltage, because for the inductors, we are always using, our interest will be on the initial current. That should be for the inductors, whereas for the capacitor, yes, we are interested on the initial voltage. Yeah. Okay. I think we have learned about this concept before in last week's lecture. Yeah. So for inductors, always related to the initial current. So for the capacitors, will be based on we will be using are going to use its initial voltage value. Yeah. Okay. So let's have a look. What should be the circuit's condition when t less than 0? Yeah. So as I mentioned before, for t less than 0, this is a short circuit. So when it's a short circuit, we can ignore the effect of 15 ohm and the 2 Henry's component. Yeah. So by right, your circuit for the case of t less than 0, it should look like this. This is your 10 ohm. That should be your 3 Henry inductors. Okay, that should be a short circuit like that. Okay, so that should be the condition of the circuit for t less than 0. Okay, hopefully you understand this concept very well. Yeah. Okay, so from these conditions, we can simply use it to find the initial current for the 3 Henry and 2 Henry inductors. Okay, so for 3 Henry inductors, we're going to have for the 3 Henry inductors, which is I 3H of 0 negative, we can find the initial current. Sorry, I apologize. I need to because this is a short circuit, right? For t less than 0. I made mistakes here, sorry. Okay, that should be no condition. There should be no inductors here, supposedly. By right, we're going to have just a short circuit. Yeah, just a short circuit here, just like that. Okay, that should be the correct version. Yeah, sorry for that, because I missed something here. So, it's supposed to be a short circuit because for t less than 0, we believe that the circuit has been in stable state condition for a very long time, because the source is a DC, right? So when the source is DC, we know that for the inductors, when we have a DC voltage, you're going to have a short circuit. For a capacitor component with a DC current, the capacitor will be an open circuit. Okay, so that should be the concept that we have done before in electronics. So we're going to apply it again here. So then you're going to have a short circuit for the inductors. Okay, so we can find the initial current for the 3 Henry inductors by calculating the current here, which is the IT. That should be the 100. So the IT value shall be equals to 100 over 10, which will give us a 10 amperes current. So the I3 Henry initial current flowing in the circuit shall be equals to 10 amperes current. Yeah. All right. And how about the 2 Henry's inductors? So for 2 Henry is in this particular branch. So we know that for 2 Henry inductors, the current for that component will be equal to 0 ampere. Okay, because the current will pass through this branch, the short circuit, it won't pass this branch. Yeah. So due to that, there should be no current flowing through the 2 Henry inductors. Yeah. So that should be the initial value for 3 Henry and 2 Henry inductors. Right, which answered the question number 1. Okay. All right. So for number 2, determine the circuit current IT for t bigger than 0. Okay, for t bigger than 0. So for this, you need to sketch the circuit's condition for t bigger than 0. So we know that for t bigger than 0, the circuit should be in a closed, in open conditions. So when it's open conditions, or we're going to have that current will pass through the 15 ohm and 2 Henry inductor. So we can then sketch in time domain first, the circuit's configuration for t bigger than 0. Yeah. So for t bigger than 0, if we can write here, the circuit condition in time domain. Okay, in time domain, you're going to have a this 100 volt. Okay, so we're going to have a resistance of 10 ohm. I apologize. Then we have a 3 Henry of inductors. Then we have these 15 ohm of resistors, and we have a 2 Henry of inductors. Okay, so that should be the case of your circuit. Yes, in time domain. Right. So when we transform into the S domain, okay, because if we go back to the questions, is to find the input current IT for t bigger than 0. What is the input current? Should be this current, yeah, this current. So for that, we need to find the IS first. Yeah, need to find the IS. What is IS? IS is the current inside the loop. So we need to transform into the S domain. So we're going to have the 100 volt shall be equals to 100 divided by S. Okay, and we have the 10 ohm resistors should be there. So for 3 Henry inductors, so we're going to transform it into the impedance of SL value. So S times L, L is 3 Henry, so we're going to have 3S. Okay, remember that for the inductors, since for the I is 0 negative, for the 3 Henry is 10 amperes just now. Okay, so we need to use it. Yeah, so we're going to have a voltage source in series with this impedance, the polarity is negative to positive. Okay, and the formulation for the voltage source is Li 0 negative. So L is 3 Henry, I is 10 ampere, so the voltage value is 30 volt. Okay, this comes from the formulations of Li 0 negative, yeah. Okay, and then we have the resistors here, which is 15 ohm. And for the 2 Henry, we don't have any voltage source because the initial current just now is 0. So simply you're going to have 2S as the impedance, yeah? So that should be the circuit which has been transformed into the S domain. So from the time domain on the left-hand side, it is now transformed into S domain here on the right-hand side. Okay, so we know that the current is said to flow inside your circuit. So that should be the IS. Yeah, so we need to find the IT, right? So IT basically is the inverse of Laplace transform of the IS. Okay, so using the KVL, yeah, KVL, you have to apply for this circuit. Okay, so you're going to have that the circuits will be 100 over S minus 30, sorry, plus 30. Okay, this is the contribution for this voltage source, so plus 30. So then it should be equals to 10 ohm of IS plus 3S plus 15 plus 2S of IS. Okay, so that should be your equation for the KVL. Okay, so we're going to have a 100 plus 30S over S. And this one can be written as IS, okay, IS, okay, and we're going to have it as equals to 25, yeah, 25 plus 5S. Sorry, my apologies, it's a multiplication, yeah, sorry. Right, need to erase this. Okay, so it's multiplication, right? And then we're going to have IS shall be equals to 30S plus 100 divided by S of 5S plus 25. Okay? Right then. So we need to do the partial fraction to find the IT. Okay, so you're going to have a IS, okay, shall be equals to 6S, okay, plus 10. I'm taking out the 5 here. I'm taking out the 5. So that should be equals to S and S plus 5. Okay, so I think you can try to solve this on your own, which is going to have A over S, A over S plus B over S plus 5. Okay, so you need to find the A and B, yeah, based on this method of partial fraction. So from that, you can find the IT by doing the inverse of Laplace transform for the obtained IS, yeah. All right, so I hope you can do it on your own, yeah, on finding the A and the B. Okay, that should be the IT. And okay, that answered the questions here. And finally is to find the V naught T. Okay, so V naught T basically is the voltage across the both the capacitor and the inductor. Sorry, the inductor and the resistor, sorry. V naught T is the voltage across the inductor and also the resistor. That should be the V naught T. Okay, so from here, we know that the IS has been obtained just now, right? So your V naught S, yeah, in the S domain shall be equals to the current of IS multiplied with the summation of the 15 ohm and 2 Henry's impedance. So it should be 15 plus 2S. Okay, should be 2S, yeah? Should be 2S. Okay, that should be how you obtain the V naught S. So IS is based on this. So you're going to have the V naught S shall be equals to 6S plus 10 over S plus 5 multiplied with 15 plus 2S. So again, this is to be based on the partial fraction. Okay, do the partial fraction to find the V naught S, and then you can simply do the inverse of Laplace transform to get the V naught t as requested from the questions. Okay. Okay. So I think the problematic part will be only on the transformation of the components lah, yeah, on the inductors and also the capacitors, and also the addition of the addition of the voltage source or the current source in series, the impedance of the capacitance or the inductance, yeah. And the rest is just applying the KVL or KCL and sketch the circuit to find the related or requested parameters from the questions. Okay, that's all for this chapter 5. I think we have end up the chapter 5. Yeah, correct. So we have end up the chapter 5 by this example just now. So from next week onwards, which is on week 11, we're going to proceed with the filters. Yeah, with the filters. So for the filters lectures next week, will be about 2 weeks lectures for the filters. We're not going to have a online classes. I have the videos for these filters topic, which have been prepared during the last semesters. So I'm going to just upload these videos in the YouTube, and you can learn it from these videos straight away. Yeah, so there should be no classes or online classes for this coming 2 weeks. Yeah, right. Okay, so I think that's all for chapter 5. And as promised, we are going to have a tutorial session for chapter 5 now. Okay, I've uploaded the questions in the Google Classroom, so I believe that most of you have tried to look at it, try to answer it. Okay, so let's have a look at the tutorial questions. Yeah. Okay, any more questions before we end the class? I mean, before we end the lectures? Any questions?
No, Doctor.
No questions. Yeah. Okay. Thank you very much. Okay. So now I'm going to proceed with these tutorial questions. Okay, so let's have a look at tutorial 6 of these questions. Yeah, so I've uploaded this in the YouTube. Sorry, not in the YouTube. I apologize. In the Google Classroom. Okay, maybe of this because of this weekend blues. Yeah, so that's a problem. Okay, tutorial 6 of Laplace Transform. This is the question that have been posted in your Google Classroom. So for information, these tutorial questions, both questions were actually the excerpt, yeah, from the previous tests and final exam questions. So I just we make it just for you to make yourself familiar, yeah, with the questions, with these problems, yeah, related to the Laplace transform and its applications. Yeah. Okay, then let's have a look at these questions. We are given these system as shown in the figures, where we have this input of xt and the yt input, which subsequently being the input to the qt and rt system. Okay, and it is then added, yeah, added to produce a zt. A zt will then pass through the differentiator, and then we are getting the output, the system. Yeah. Okay, so based on that, we are also given the system's equation, where we have Qs equals to S plus 3 divided by S squared plus 2S. And the Rs will be equals to, or given to be equals to S over S plus 2. That should be the Rs. Okay. Then if xt is given to be a delta t, and yt is equals to ut. So you need to determine these parameters. The first one is to find the zt. Okay, you need to find the addition of the systems of qt and rt's output. Okay, so you need to actually understand what should be the relationship between the input of xt, the systems of qt, YT and RT. Okay, I was actually disturbed by students try to enter the class, so I have to permit, I have to give access to them then, yeah. Okay, so hopefully next time you have to come to the class earlier, yeah, before 11 or 5 minutes before, after 11. Okay, I have been very kind to you before, so please, yeah, please discipline yourself, yeah, it's very important, yeah. Okay, let us proceed with these questions. Okay, so from this diagram, so let me have a tool. Let me see where's the tool. Okay, have a tool there. Right. Right then. So from this relationship, we know that the ZT, okay, the ZT by right shall be equals to XT convolve with the QT, right? So that should be the relationship. So when we have this pattern, the relationship in the time domain should be XT convolve with the QT, okay? Plus the YT input convolve with the RT. Okay, so that should be a relationship in time domain, yeah, for the ZT. Okay, so from here, well, we can then do the Laplace transform to find the ZS, because the question is to find the ZT, yeah? So we need to find the ZS first, then only we do the inverse of Laplace transform, which is easier for us. Because why? Because the QS and RS have been given. QS is the S domain or S transform for the QT. RS is the S domain or S transform for the RT, yeah? So we can then write that in terms of Laplace transform, this equation here will be equals to ZS shall be equals to XS multiplied with the QS plus YS multiplied with the RS. Yeah, this is the properties of convolution in Laplace transform. Yeah, when we have a convolution in time domain, in the S domain, it should be a multiplication. Yeah, so that's what we have learned before. Okay, now we can substitute the QS and RS together with the transformation of XT and YT in the S domain. So we know that for the XT of UT here, in the S domain, it should be equals to 1, while for the UT in the S domain, it should be equals to 1 over S. Yeah, this is based on what we have learned previously. You can refer to the table to confirm on this transformation, yeah, for the delta function and for the step function. So for this, we can have that the ZS straight away will be equals to XS of QS or XS multiplied by QS, which is equals to 1, which is the XS, multiply the QS, which is S plus 3 over S squared, yeah, S squared plus 2S. Okay, plus, sorry, yeah. Okay, plus with the YS, which is 1 over S, so 1 over S multiply with RS, which is S divided by S plus 2. Okay, so that should be your ZS that you have obtained successfully. So this can be cancelled out, the S, and this can be cancelled out. So we're going to have, S plus 3 divided by S squared, so S or S plus 2, sorry, plus 1 over S plus 2. So you need to do the partial fraction for this term. We're going to have A over S plus B over S plus 2 plus 1 over S plus 2. Okay, so for this transformation of changes of terms from this, from this form into partial fraction form, so you're going to need to find the A and B. So to find the A, okay, you're going to have multiplication with S. It's going to have S plus 3 over S plus 2 equals to A plus B over S plus 2. So substituting S of negative 2, you're going to have that A shall be equals to, sorry, this S, I apologize, not S plus 2, it should be S, yeah? It should be 0. It should be 0. Okay, sorry for that. F S equals to 0, so we're going to have A shall be equals to 3 divided by 2, yeah? Okay, the same things apply to find the b. So b need to multiply both sides with s plus 2, sorry, with s plus 2, right? Yeah, s plus 2, multiply both sides with s plus 2. So you're going to have s plus 3 over s shall then equals to a over s plus 2 plus b. Okay, this b, yeah? Okay, so substitute s of negative 2. Okay, so we're going to have b shall be equals to negative 2 plus 3 over 2. So the answer shall be equals to half positive. Please check for me whether I'm doing it correctly. S of negative 2, so we have s plus 3, yeah, s plus 3 over s plus 2. Yeah, so we're going to have s plus 2, correct. Okay, then we substitute s of negative 2. So negative 2, so that should be negative down here. So the answer should be of negative 2. Okay, so negative 2. So that should be the b value. So for that, we're going to have the equations of zs. If you can write down here, zs shall be equals to a, which is 3 over 2. Yeah, so 3 over 2s. b is negative half minus 1 over 2 s plus 2. Okay, and they have this term just now, which is 1 over s plus 2. Okay, so we can simplify it further because we have the same terms there. So we have 3 over 2s plus 1 over 2 of s plus 2. So that should be the zs that have been obtained. So from here, we can find the zt by using the inverse of Laplace transform. Same things applied here, use the inverse of Laplace transform. We have to have the zt shall be equals to 3 over 2 of ut plus 1 over 2 exponential negative of 2t of ut. So that should be the answer for your zt. Okay then? Okay, yeah? So that should be your zt, yeah? Okay, so that answer question 1, part 1 of the question. So next one is to find the Laplace transform for the differentiator output. This is the one, the questions here. Find Laplace transform for the differentiator output. So I need to go back to this part. So I'm going to erase it, yeah? Yeah, I'm going to erase this. Hopefully you have copied it just now. I'm going to erase it. Okay, sorry, yeah. Okay then. Good. Okay. So need to find the Laplace transform of differentiator output as stated here. Laplace transform for differentiator output. So let us put that the output here is yt. Yeah, let's put it as yt. Okay. So need to find the what should be the ys. Yeah, that should be the questions. Okay. So we know that from this relationship, yeah, between zt and yt, we have differentiator here. So the equation that relates both of them shall be yt shall be equals to d over dt of zt. Yeah. Okay, that should be the relationship between the zt and also the yt. Okay, so we can do the Laplace transform for both sides, left and right. Okay, so we are supposed to get ys, and that should be based on the differentiation properties, which will give us s of zs, yeah, minus z0. Okay, this is zs, yeah, zs. This is z0. Basically, this is zt, yeah, when t equals to 0. Yeah, hopefully you understand this. We have discussed this last week. Yeah, so z0 here is your time domain value, or zt, when the value of t equals to 0. Okay, so how to find z0? How to find z0? That should be based on this equation that we have obtained previously from part 1, right? Yeah, because this is zt. Okay, so to find 0 for that equation, simply we just substitute t equals to 0. Okay, sorry for that. T equals to 0. So we are supposed to get the value of zt, sorry, z0, yeah, z0 shall be equals to 3 over 2, okay, plus half, supposedly, yeah. And for this, the value shall be equals to 2. So that should be the value of initial value of t equal to 0 or z0, yeah? So we substitute the z0 straight away in this equation. So we are going to get ys shall be equals to s. Zs has been obtained previously, so that should be your zs, yeah? T over 2s plus 1 over 2s plus 2. We just copy it back here. We're going to have it as 3 over 2. Okay, 3 over 2s plus 1 over 2 exponential. Sorry, my apologies, sorry, I made mistakes. Okay, 3 over 2s plus 1 over 2s plus 2. Okay, plus 1 over 2 s plus 2, okay, minus z0 that we have obtained just now equals to 2, minus 2. Yeah, minus 2. So basically, you're going to get that finally, your ys okay, your ys shall be equals to 3 over 2, okay, plus s over 2, s plus 2, minus 2. So that should be your ys, yeah, which is a Laplace transform for the output of your differentiator. Yeah, so we can simplify it by solving 3 over 2 and 2, yeah, so you can do it on your own. Okay, is that okay? Have you do you understand this example? I mean this tutorial solution? Any question for this solution? No? Okay, if there's no question, we can proceed with the next questions here. Okay, so I believe we have done this before, right? Yeah, okay, we have done this before, sorry. So we're not going to proceed further. So we have done it in the previous example in the lecture session just now. We just skip this question. Okay, so we proceed with the next questions here. Okay, these questions we are given the xt, which is illustrated in figure question 2a as stated in this diagram. You need to determine the xs using the Laplace transform test provided in the appendix 1. Okay, so we are given the signal of xt. So from this xt, you need to find the xs, yeah? Okay, so how to solve this? Basically, you have to find out what should be the mathematical equation for the xt, yeah? Based on the functions that available in your attachment or in the appendix 1, yeah, based on the parameters or based on the signals that available, yeah. So for this, we can write the xt by right should be in terms of a ramp function and also in the step function, yeah. So if I can do it for the first ramp functions here, okay, so we divide it into two parts, this function first. So for this ramp function, we can write it as equals to, so what should be the slope value? Is 2 divided by 2 is 1, yeah? Slope is 1. So we're going to have just a straight line of t, yeah? And the step function involved here will be between 0 and 2. We're going to have ut minus ut minus 2. Okay, that should be for the first signals number 1, which is the ramp function. Whereas for the second step function, which is between 2 and 3, we're going to have 2 of ut minus 2 minus ut minus 3. Okay, so we're going to have these equations here. So we can rewrite the xt based on these two equations of the signals. So we are going to get xt shall be equals to t of ut minus t of ut minus 2, okay, plus 2 of ut minus 2 minus 2, sorry, minus 2 minus 2 of ut minus 3. Okay, yeah? Right, so if we base on these equation based on these terms, when we refer to the Laplace transform table, the TUT can be obtained. We can do the Laplace transform for TUT. For the TUT minus 2 can also be obtained, and also for the UT minus 3 can also be obtained. But the problem is these terms here. Yeah, because if you want to do the shifting, or you want to use the shifting properties, you need to ensure that both the ramp and the step do have the same shifting value. For instance, for this particular terms, it's supposed to be t minus 2, ut minus 2, supposedly. Okay, so we cannot transform from time domain to a Laplace or to the S domain by just based on these terms. You have to modify it to be look like this, so that we can do the shifting properties, yeah, in this transformation. So what we have to do, we have to modify the second terms here. So we're going to have to modify it to be look like this, where the t ut minus 2, okay, and that should be equals to t minus 2 plus 2 of ut minus 2. Am I right? Yeah, because the effect of negative 2 and plus 2 will result of a zero value, so there should be no effect at all. Yeah, but we just create it. Yeah, we just create it for the sake of to produce this form of term. Yeah, so we can then separate it to be look like this, where we have t minus 2 of ut minus 2, and then we have 2 there, plus 2 of ut minus 2. Okay, so that will be the modification that need to be done to transform this TUT minus 2 into something that can be, or into the terms that can be transformed into Laplace by using a shifting properties. Yeah, so this is the one. So we need to rewrite it back based on what we have done before. So we're going to have TUT minus t minus 2 of ut minus 2. We have negative sign here, so it will result in negative sign also. Minus 2 of ut minus 2 plus 2 ut minus 2 minus 2 ut minus 3. Okay, so from here we notice that these terms and these terms are the same. They have negative, they have positive, so it can be cancelled out. So left only with TUT minus t minus 2 ut minus 2 minus 2 ut minus 3. So from here we can do the Laplace transform. Okay, so we can do Laplace transform. That should be the Laplace transformation xs. Okay, xs shall be equals to, so TUT will give us 1 over s squared. These terms here we have a shifting of 2. We're going to have minus 1 over s squared exponential negative 2s, and for that we're going to have negative 2 over s exponential negative 3s. So that should be the answer of the xs of the given xt, or Laplace transform of the given xt. Okay then. All right, yeah. Okay, good. Next questions, number 2. Right. Prove the answer in question 2a1, the previous question, using Laplace transform differentiation and time shifting properties with x0 equals to 0. Okay, so we are given the x0 value. X0 basically is a value of xt, yeah, when t equals to 0. So basically we can also deduce it from this diagram, because from this signal we know that the xt value when t equals 0 is equal to 0. Yeah, this value here is 0. So without giving us this information, we can also reduce it, or we can also deduce, or I can say obtain it from this signal of xt. Yeah, because at t equals to 0, the x0 will be 0. Yeah. Okay, so in these questions, we are requested to prove the answer in question 2a1 using Laplace transform, differentiation, and time shifting properties. So specifically, we are requested to use a Laplace transform, differentiation properties, and time shifting properties to find the Laplace transform for the xt. Okay, yeah, so you got the idea there. Previously, what we did is we just transform it straight away from the signal xt. We find the equation of xt, and then we do the Laplace transform. But for the second part here is that we need to differentiate the xt first. because it's given here, we need to use, specifically, we need to use Laplace transform differentiation and time shifting properties. So basically question 2 is just to prove that by using this technique number 2 here, we can also get the same answer as part 1 just now. Yeah. Okay, so let us proceed with this solution for part 2. I'm going to erase this. So yeah, let me erase this one first. Okay, that should be easier for me then. Okay, good. Okay, so we need to differentiate this signal, yeah? So what I'm going to do now is I want to differentiate it now. Okay, all right. So that should be my x, sorry, this should be my dt, d over dt of xt, yeah? Differentiation for the xt. Okay, so this is your straight line having a slope of 1 or equals to t, the equation for this line. So from 0 to 2, this is 0, this is 2, this is 3, yeah? From 0 to 2, when we differentiate this straight line, we're going to have a constant, yeah? So the constant, since the slope is 1, so the constant will be having an amplitude of 1, yeah? So that should be your constant, or the graph between 0 and 2, which is a result of differentiation for this straight line of having slope of 1, yeah? Okay. From 2 to 3, because it's a constant value, so that should be 0 between 2 and 3. There should be no value for the d over dt of xt. But at t equals to 3, at this position, we notice that there is a step, yeah, a step from 2 to 0. Yeah, a step from 2 to 0, in which if we differentiate this step here, we are going to have an impulse. Yeah, we're going to have an impulse then, but the impulse is having a negative direction because we can, based on this, we are said to have a step down transition, yeah, from 2 to 0. So for that, we're going to have a negative 2 of delta t as a result of your differentiation, yeah, for at t equals to 3. So that should be the results of your differentiation of the xt. And from here, we can write it accordingly, in which d over dt of xt can be written as ut minus ut minus 2. Okay, this is for this step function between 0 and 2. And need to consider this the impulse function, negative 2 of delta t. Okay, that should be your d over dt xt, yeah? All right, so now, as stated in the questions, sorry, my mistake, not delta t. I made a mistake again here, sorry for that. Not delta t. We're going to have a shifting value, yeah? Delta t minus 3, okay. Delta t minus 3, that should be the correct one, yeah? Because it's a shifting to 3, yeah? So they have a negative 3 then, yeah? Shifting to the right, yeah? Right, so now we can do the Laplace transform for both sides, left and right. So this will give us sxs minus x0. Okay, so that's why the question gives us x0 because need to be used here. Okay, but without giving us the x0, we can also deduce it from here, also 0 as mentioned before. Okay, equals to ut when we do the Laplace transform, we're going to have 1 over s. For this, we're going to have 1 over s exponential, negative 2s. And for the third one, delta t minus 3, if we refer to the table, supposedly going to have a, let me see the table, yeah? I have my table just now. Where is my table? Laplace transform table, let me check. Where is my Laplace transform table? Okay, this is the one, my Laplace transform table. For delta t minus a is with the negative exponential negative as. Okay, so we're going to have a negative 2 exponential negative of 3s. Okay, that should be the transformation for delta function that shifted by 3 units to the right, yeah? Okay, so from here, we know the x0 is 0, so we just cancel it out. Yeah, is 0. So we're going to have xs. We can bring the s to the right-hand side. 1 over s squared minus 1 over s squared exponential negative 2s minus 2 over s exponential negative 3s. So that should be the xs obtained by using the second technique. Yeah, when we differentiate it and we do the Laplace transformation. So basically, the answer that you obtain in part 2 should be the same as part 1 just now. Yeah, you can check it. Supposedly it's the same. Okay, any more questions? Any questions for this example? No? Okay, if no questions, let us proceed with these questions on the circuit. Yeah. Okay, so we are given an electrical circuit as shown in diagram here. The switch in the circuit has been closed for a very long time. Okay, we have a circuit, we have a switch here. Yeah, closed for a very long time, and it is opened instantaneously at t equals to 0. Okay, so then we can deduce it for the case of t less than 0. Okay, in time domain, yeah, for t less than 0, the switch basically has been closed for a very long time, yeah, which is for t less than 0, and it is open at t equals to 0. Yeah, so when t equals 0, the switch is open. So that for t less than 0, we can then sketch the circuit in time domain, which will be look like this. Okay, this is 10 volt. So for t less than 0, that should be a short circuit. Yeah, the 1 Henry will short circuit because it has been there for a very long time. Okay, so we have a 2 ohm resistor, then we have short circuit still, yeah, because there should be no effect of 2 Henry. Okay, so the current will pass through this switch, yeah, so it will pass through the switch here, so that should be the circuit's condition for t less than 0. Okay, so from here, we can use the circuit to calculate the initial current for the 1 Henry inductor. Yeah, 1 Henry inductor, because the circuit is in this stable condition for a very long time. So we can then find the initial current for the 1 Henry, which is the current of 1 Henry inductors 0 negative, which is the initial value for the 1 Henry inductors. Yeah. Okay, this can be calculated by simply calculating the current IT inside the circuit, yeah, at this condition. So from this, we know that the IT shall be equal to 10 over 2. That will give us 5 amperes current. So it means that the 1 Henry's initial current will be then equals to 5 amperes, same as this 5 amperes current. Yeah. Whereas for the 2 Henry's inductor, because the circuit is closed or is short circuited down here, so there should be no current pass through the 2 Henry's inductor. So we can say that for the 2 Henry's inductor, the initial current for it shall be equal to 0 ampere. Yeah, there should be no initial current for the 2 Henry inductors. Okay, that should be the case. So from here, we need to find, because the question needs us to find the Laplace transform, use the Laplace transform to calculate the IT. We need to find the IT here, yeah, the IT in the circuit for t bigger than 0, I believe. Yeah, this is for t bigger than 0. Okay, so from here, we can sketch the S domain. Yeah, the S domain for this circuit. Okay, so we are going to get, if I can use this side, yeah. So we're going to have the 10 volt should be now equals to 10 over S. Okay, 1 Henry will be now returned to be SL, which is S only because L is 1 Henry. Yeah, we go back to the equations, yeah. Okay, in which we have V equals to L di dt. Just recall back lah, yeah. So the VLS shall be equals to SLI LS minus Li 0 negative lah. Okay, so that's how we have this equation. Okay, remember that we have initial current, yeah, just now for the 1 Henry, so 5 ampere. So we're going to have one voltage source in series. Yeah, so the value is 5 times 1, yeah, from this relationship, 5 times 1, which is 5 volt, yeah, 5 volt. Then we have a 2 ohm resistors, should be there. This is 5, this is S, yeah, not 5, yeah, S. Then we have 2 Henry, just 2 Henry inductors here. Short circuit, so this is open circuit, so the current can pass through 2 Henry. So because there is no initial current for the 2 Henry, so we just have the impedance here. So the impedance is 2S, yeah, not 2S, yeah, 2S, because SL, yeah, 2S for the inductors impedance, yeah. So we're going to have this circuit. Okay, so that is a circuit that's been transformed into the S domain. So now you can find the IS first. IS is the current inside the loop by using the KVL, and from this IS obtained, you can then calculate the IT, which is the current flows in this particular circuit. Okay, so let us use the KVL to find the IT or IS, sorry. Okay then, or can I just erase this part only? Okay then. Okay, so now okay, so we can then use the KVL, yeah, use the KVL, Kirchhoff voltage law. So the equation for this S domain circuit will be equals to 10 over S, the voltage source, plus 5 volt. Okay, 5 volt of the voltage source for the inductors, 1 Henry, equals to S plus 2 plus 2S multiplied with the IS current. Okay, so you're going to get that 10 plus 5S over S equals to 3S plus 2 of IS. So we're going to have IS shall be then equals to 10 plus 5S divided by S of 3S plus 2. Okay, so we need to do the partial fraction to find the IS, and then we need to transform it, the inverse transform it back to the IT. Yeah, so we're going to have it as A over S plus B over 3S plus 2. Okay, so that's how you find the A and B, and subsequently we can find the IT. Yeah, so I'm going to use this side here. Okay, so from here we can write that to find A, okay, to find A, what you have to do, multiply both sides with S. So we are going to get 10 plus 5S over 3S plus 2 shall be equals to A. Okay, I don't want to write the B, so because nothing much difference, yeah, will happen then. So substitute S equals to 0. So we're going to have A shall be equals to 10 over 2, which is equals to 5. Yeah, so that should be the value of A. Whereas for the B, we need to multiply both sides with 3S plus 2. So we're going to get 10 plus 5S divided by S. And we just write it as B only, yeah, for the A. There's nothing much difference there. So substitute S of negative 2 over 3. So you're going to get your B shall be equals to 10 minus 10 over 3 divided by minus 2 over 3. Okay, so we're going to get what then? The answer, so 30 minus 20 is 20 over 3 minus 2 over 3. So we're going to get the answer as equals to negative 10. Yeah, 30 minus 10 is 20 over 3 minus, correct, this is 10, yeah, negative 10. Okay, so from here we can write that the value of IS will be 5 over S plus, or negative, yeah, minus 10 over 3S plus 2. Okay, so that should be your IS, yeah. Okay, so for then, you can do it the inverse of Laplace transform. Yeah, we're going to get the IT shall be equals to 5 UT minus 10 over 3 exponential negative 2 over 3t of ut. Yeah, this is 3. Yeah. Okay. So that should be your IT. Yeah, the inverse of Laplace transform for the current just now. Okay, so that should be the current. Current in your circuit. Yeah, in the loop. Okay, finally is to find the VRT. So what's VRT? VRT is the current across the 2 ohm resistor. So simply we just use the Ohm's law. Yeah. So the VRT will be equals to 2 multiplied with IRT, which is IR is obtained just now. This is your RRT basically. Sorry, this is the IT. My apologize. Yeah, this is the IT. Okay, but the IRT is similar to IT. Yeah, so IRT is similar to IT. So we can just use this IT into this equation. We're going to have 10 of ut minus 20 over 3 exponential negative 2 over 3t of ut. Okay, so that should be the answer for this example number 2. Okay, so that's all for this tutorial session for the Laplace transform and its application. Okay, guys, any question for this example? No questions at all? Okay, I hope you understand it clearly on this example. Okay, so I just want to remind you again that we're going to have a quiz tomorrow. So tomorrow the quiz will start at 10 o'clock and it should be ended at 10:30. Yeah, so no class tomorrow, just a quiz. Yeah. So basically, this should be the 3rd quiz, and this will be the last quiz for the semester. Yeah. So we are going to have only 3 quizzes. Yeah, 3 quizzes. We have the first one is on signal. Yeah, part chapter 1, basic signal and system. Number 2 is on Fourier series, and number 3 will be on Fourier transform. So 3 quizzes altogether, which will give 10% of your final marks. Yeah. And then only quiz tomorrow, 10 to 10:30. No lectures. Yeah, we're going to end the class at 10:30. And for next coming 2 weeks lectures, yeah, in 2 weeks lectures time, starting from next week, there should be no online classes. Okay, because I'm going to provide the videos, yeah, which will be uploaded in the YouTube for the topics of filters, chapter 6. Yeah, you can try to read or learn on your own. And if you face any problems, any difficulties, you can always PM me, yeah, for further informations or for any assistance. Okay then, if there's no more questions, I'm going to end my class today. Yeah. Okay. So thank you very much again to all of you. Okay, and we need to meet you. Yes, the questions then. Okay,
I have a
okay.
question in the group assignment.
Okay, come again. I cannot hear you clearly, Rahman.
Do you hear me clearly now?
Okay, then. Okay.
Yeah, Doctor. I have a question in the group assignment.
Okay.
Can we use the Laplace transform?
No.
Solving the...
No, you have to use a chapter 1, the basic convolution, to solve the problems. Yeah.
Okay. Thank you.
Thank you very much. Okay, bye bye, guys and girls. Going to meet you again in 2 weeks' time. Yeah. Thank you.